We'll have 4 papers and just 2 short messages. The first paper, we want to really thank Peter Stair, because Abaya and myself asked him to put together something a little bit more important than what he had presented. We wanted to recognize that as a special oral, and it didn't appear in the proceeding, but so let's say thanks to Peter Stair for the extra work he has been put. And then the last talk of this afternoon has been cancelled, but the good news, this is the bad news, the good news is that it has been replaced by a, let's say, a last-minute presentation put together by Bert Weckhuysen. So we will not hear something about Fischer Tropsch, but we will hear something about zeolites and some brand new results. So I think it probably was worth it. So there is probably no need to introduce Peter Stair for what he has been doing in Raman, in situ and time resolve, and I think it's a very great way to set the scene for this afternoon. So thank you very much.
Okay. Okay. So thanks very much for the chance to speak. We were talking about the printed program, and it has a few deficiencies, as we all know. So Bert will be under no disadvantage that his name is not associated with the talk at the end of the session, because nobody's name is associated with any of the talks. And so it's remarkable that we can even find each other. So this talk is actually sort of an advertisement. There are 3 posters on Raman spectroscopy at the poster session tonight. And all I'm going to do is to give you a little taste of each of them. And this will be in the form of a brief advertisement, as I said. And for the gory details, you can go to the poster session if you can find the posters in the list. All right, so this is about Raman spectroscopy, looking in reactors, and of course the interest in Raman spectroscopy and the value of Raman spectroscopy is that not only can we see the catalyst, but we can also see the molecules with one measurement. And there are, of course, few analytical techniques that can look at both sides of the heterogeneous catalytic interface. The first poster and the first little vignette I'm going to tell you about is some new work, unpublished, on time-resolved ultraviolet Raman spectroscopy of coke formation. Now, those of you who have followed any of our work know that we have been working on coke formation for some time. And one can sketch out a schematic mechanism of the coke formation process in, for example, the methanol to hydrocarbons chemistry done over zeolites. This is a talk that has a little bit of zeolites in it. I don't know whether it was included in the Houdry list this morning. But we've seen a number of these individual molecular species, but what we found typically was that as we ran the reaction, we get a very complicated mixture very fast. And it's very difficult with just vibration spectroscopy to say very much about the details of the molecular composition of these mixtures. So we thought that we would try something a little different. The strategy was, if we could stop the reaction fast enough and only look at the very early stages of the coke formation reaction, that perhaps we would have a chance of seeing something simpler than what happens even after a few seconds. So the idea was that we would use an infrared laser through a window to heat the zeolite. And this infrared laser we can move around, and the zeolite absorbs quite nicely the infrared. And the advantage over using a conventional oven to heat is that we can heat and cool very quickly, so that we can look at reaction times that are on the order of milliseconds as opposed to seconds to minutes in the conventional system. So if you like, this is millisecond contact time, but it has nothing to do with oxidation or high temperature. We model the heating of the zeolite with the infrared laser something like the following. we have a particle, and only a skin of the particle is actually heated. And in the way that we do this experiment, we first completely fill the zeolite with methanol at room temperature, where of course nothing happens. And then we simply pass the laser in a pattern over the zeolite bed, and then we look with the Raman spectroscopy. So it's time resolved in the sense that we heat and quench very quickly, but it's certainly not time resolved on the fly. We're not looking in milliseconds to measure the Raman spectrum. There's several interesting features about this, which you can read about on the poster. One of them is that this system, these zeolites, act like a closed system. The diffusion is so slow on the time scale of the heating that nothing comes out of these materials. So it's as though you have a fixed volume reactor with reagents in it, and you simply heat it up and look at what you're producing. And since we're using the spectroscopy to look at what's inside, it doesn't need to come out in order for us to look at the progress of the reaction. So here's an example of one zeolite. This is a somewhat higher, we're going to look at two with two different aluminum contents. Here's the one with higher aluminum content. Of course, vibrational spectra are hard to look at because there's all these peaks, and it's not, some people might say it's somewhat boring, and they'd probably be right. But if we look at the beginning here, the peaks that are showing up here are just peaks due to the zeolite, for example, this one here, and the rest of the peaks are due to methanol. And this is heating to the degree of 1% of the laser power, which is about 100 K transition from room temperature. And so this is not hot enough to do any chemistry. As we proceed to higher laser powers, then you can start to see things build in, and you can start to see the methanol disappear. So just like I said, it's like you have a fixed volume reactor, and you simply drive the reaction and look at what's in the reactor. This is a different aluminum content. This is considerably lower aluminum content, but the same story. The methanol tends to disappear, and we see some new peaks that grow in. Now, if we look in detail and try to make a comparison between these two zeolites, we see something interesting. So here is a case where we've superimposed the Raman spectra after some period of heating for the two different zeolites, the high aluminum content and the low aluminum content. And the extent of reaction is identical. That is, we've removed the same amount of methanol in the process of the reaction, but remember, none of it has come out. It's all still in the zeolite in one form or another. This is a zeolite band, which gives us a normalization. So this gives us a way of normalizing these two spectra to each other, so we can directly compare the intensities. So you see that the products that are made in the zeolite in these short contact times are quite different. And if we use our knowledge of what these kinds of spectra look like, we can say that in this higher aluminum content zeolite, we form polyaromatic hydrocarbons, which have a sort of a one-dimensional topography. And you can go to the, or topology, so that you can go to the poster and see what that means. If we look at the lower aluminum content zeolite, now we form polyaromatics, which have a sort of a 2D topology. And again, you can go to the poster and see what that means. But the message here is that even though we're talking about MFI zeolite, and we're talking about the same reaction under the same conditions where everything is kept inside the zeolite, you have quite a different product selectivity in these two cases, and it comes out quite clearly in the vibrational spectroscopy. All right, the next poster I want to just quickly introduce has to do with looking at vanadium. And some of you may know that we've spent some time looking at vanadium and aluminum as a model system for both dehydrogenation as well as oxidative dehydrogenation. And of course, what we're interested in with the Raman spectroscopy is to get a handle on these guys, these vanadium species, or vanadium species, which are supported on the alumina support. And one of the things that we found in the past and have published about is that if we use a UV laser to make the measurement, then we tend to see this portion of the distribution of species. So that we always think of this in terms of these vanadium species as being in a distribution of sizes and forms. And we're more sensitive to the smaller ones when we use the UV excitation. than when we use visible excitation. So when we use a visible laser, we're more sensitive to these bigger guys. So that when we have a mixture of these different species or speciations on the support, we can dissect it to a degree and say how much of each there is. All right, now what we were curious about is whether we could do this when we reduce the vanadium. Now people have looked at the reduction of vanadium by hydrogen in this system before, and we repeated that work using a visible laser, and what you see looks something like the following. This peak is associated with the V double bond O stretch, and this peak is associated with the bonds that connect the vanadium to the support. And what you can see as a function of the reduction temperature is eventually the spectrum more or less disappears. In particular, the vanadium disappears completely, and there may be a little residual of this peak left over. And this kind of thing had been reported in the literature previously. On the other hand, if we use the UV laser to look at it, what we see is we see some loss of intensity, but it never completely goes away. So what it's telling us is that there are vanadium species on this support which do not reduce. Even at relatively high temperatures of 700 degrees C in hydrogen, they do not reduce. And the conclusion then that we come from this measurement is the idea that there's a difference in the reducibility of the linkages that are present in these different vanadium species. All right, now, why is it that we can see something in the ultraviolet excitation when we can't see it with the visible excitation? Well, it turns out that one of the reasons is a little trick. The problem with seeing the spectrum using the visible laser is that as the sample is reduced, it turns dark. And the laser doesn't get into the sample and come out, and we don't see the scattered light coming out because of absorption, so we call it so-called self-absorption effect. And what you see is if you look at the UV vis absorbance, and I'm losing my finger's in the way. Okay. That's right. All right. So what this is supposed to show is that as the sample is reduced, the absorbance in this visible region is increasing quite dramatically. But interestingly enough, in the UV region, when we do the UV excitation, the absorbance is actually going down. So that in fact we have more sensitivity as the sample's reduced between the two wavelengths. So it shows you the utility of being able to do measurements at a variety of wavelengths. Finally, we make a connection with what happens if you do a dehydrogenation reaction. So we expect that if we dehydrogenate butane, for example, that the sample may be reduced. There's no oxygen in the feed, so we're simply doing a straight endothermic dehydrogenation reaction. And what you can see at this particular high loading is in the beginning we start out with B205 crystals, which is what this peak represents, and we still have these vanadium species. And as we reduce in hydrogen, we see that the vanadium signature goes away. We have an interesting peak that pops up in the middle, sort of the reduction, and ultimately we end up with a spectrum that looks like this with this broad lump. If we do the same thing using butane, we see again this intermediate peak, which shows up here, and ultimately we have just a hint of this broad lump when we're done. So it looks as though, at least to the degree that the spectroscopy can tell us, that the vanadium species are very similar, made by hydrogen reduction as compared to using butane as the reducing agent. If we try to look at various reduced vanadium compounds to try to get an idea what this lump might be, we find that B203 gives us a lump at just the right place to explain the lump that we see after the hydrogen reduction or the butane reduction. So the conclusion would be then that the reduced form of vanadium in this system looks like B203. This is a conclusion that comes out of all of this work, and I'm going to skip this and let you look at it on the poster and talk to Zili Wu, who did this work and formulated this conclusion. I want to finish my little vignettes with a third one, looking at resonance Raman spectroscopy, both of catalysts such as vanadium and of the supports that are holding those catalysts. And this particular work was done at Argonne National Labs using a new instrument that we commissioned about a year ago, which allows us to use a whole variety of wavelengths to excite the Raman spectra. So from about 210 nanometers up to 900 nanometers. So we have an incredible array of measurements that we can do with this instrument. That's the good news. The bad news is, of course, that on every sample you can do many more measurements than you probably should, and consequently there's a temptation to just measure forever. All of the measurements can be done in situ or under operating conditions, and we have a very efficient spectrometer for dispersing the light using any of these wavelengths that we have accessible to us. Okay, again, let's go back to the vanadium system. The question is, what new can we learn about these vanadium species if we use any laser wavelength that we would like? And the answer is given in part by this diagram. So what we're looking at here is a set of Raman spectra that were measured for different vanadium loadings. The top spectrum here is just the alumina. And as we move down, the vanadium loading increases from still a quite small loading of 0.16 vanadium per square nanometer up to a loading as large as 4.4 vanadium per square nanometer. And now what we're looking at here is we're looking at the entire range of vibrational transitions that might be of interest. So we are even capturing the OH region, which normally you wouldn't see measured in Raman spectroscopy, as well as all of the low frequency modes down here in this region. Now the spectra that I was showing you before in the previous little vignette was just capturing this region here. And this sharp prominent peak is associated with this vanadium, the V double bond. And these other sharp peaks are associated with the alumina, so you can see them up here. This particular alumina has a nice vibrational spectrum, and we can use that actually as an internal standard to get information about quantification. This little broad hump here, which you see, which becomes more apparent as the loading increases, is the second band that I pointed out in the previous vignette, which was associated with the vibrations between the vanadium and the support that it's anchored on. Now, you'll notice that there are some peaks here. So what are those? Well, those peaks are overtones of the vanadium and the vanadium bound to the surface. And in fact, we even have a third overtone at this loading up here. And you can see a hint of it in this red spectrum. So what's going on here? Well, this is a characteristic signature of the so-called resonance Raman effect. And in the resonance Raman effect, you start with a molecule which is in the ground vibrational state, and the laser matches an electronic transition up to an excited electronic state, and then is driven down to back to the ground electronic state, but with more energy and vibration. In the typical Raman case, we only see molecules that end up with one quantum of vibration. But with the resonance Raman effect, we also can often get molecules with 2 and even 3 quantum of vibration. Now, one of the interesting things that you can do from this, from the point of view of the physical chemistry of these species, is one can fit the progression of vibrational energies to a Morse potential. So here's a sort of a schematic of a Morse potential. As the vibrational energy increases, the energy gap between vibrational levels decreases. And by taking this to the dissociation limit, you get a measure of the energy or the depth of this well. So this becomes a way of more or less directly determining something like the bond energy of different oscillators in the species. So in this measurement, we not only can make an estimate of the V double bond O energy, but we can also make a measurement of the energy associated with the binding of this vanadium to the support, just from doing a spectroscopy measurement. Okay, so this shows a set of results from, in the graph over here, for 2 forms of the vanadium. If we dry the vanadium out at high temperature in oxygen, then we would call it dehydrated vanadium. If we look at it in air or we allow it to contact water, then the vanadium band has disappeared, but we still have the band associated with the vanadium support interaction. And so from this determination of the bond energies, we can see if there is a difference between the bond energy of the vanadium bound to the support versus the V double bond double. The blue bars here show you the energy that we estimate for the dissociation of the V double bond double. And the black bars show you the energy that we estimate for the pulling of the vanadium off of the support. So it's quite clear that the energy associated with this vanadium surface bond is considerably less than the V double bond double. So that one's intuition would say, of course, that this is the place where chemistry will occur because the energy is lower to do the dissociation. And this is now obtained from directly from a spectroscopic meter. Now I mentioned that we also look at supports. So another thing that we can do with this measurement is look at, or with the Raman spectroscopy, is to look at the alumina. And this is a comparison of 3 aluminas. So here is theta alumina, which is the highest temperature transition alumina, alpha alumina, which of course is the low surface area sapphire structure, and gamma alumina. So there are some quite interesting features to these that we don't quite understand. All these sharp peaks here are associated with isolated hydroxyl groups on the alpha alumina. This sharp feature here is due to isolated hydroxyls on the theta alumina, and we have a similar sharp feature on the gamma, and those of course have been seen before. Interestingly, if we look in the low frequency region, we also see structure associated with gamma alumina. Normally gamma alumina is said to have no Raman spectrum, and indeed it's very weak. By comparison, these are the Raman peaks due to respectively O2 in the air and N2 in the air. And you can see that they are much stronger than the alumina. Typically, we don't worry about contributions from the gas phase to Raman measurements, but in this particular case, because the solid is such a weak scatterer, in fact, it's weaker than the spectrum measured from the air itself. Finally, I'd like to just comment on a new synthetic approach that we have used to try to simulate various supports and supported catalysts, namely atomic layer deposition. And in the poster, you'll see an example of the chemistry that is used to make these layers. But the idea here is that one could start out with a little tube that is made of aluminum oxide by electrochemistry, coat it with pure alumina so as to form a pure alumina starting point. And then if, for example, we were interested in, as a model system, vanadium on titania, we might coat a blue layer of titania and then finally finish off with vanadium. So that this sample would look like a vanadium on titanium material. But it's all done by this atomic layer deposition process, including the formation of the support. So this is not a conventional titanium. It's in fact, an amorphous titanium. Now, we wondered if at some point, by heating the support, namely this amorphous titanium, if it would crystallize. And this shows an example of that. So the spectrum here is the spectrum from the titanium by itself. And after the titanium has been heated in the presence of vanadium, one sees that a series of peaks show up. And if we compare the positions of these peaks to, for example, in this case, anatase powder, it's quite clear that we have formed anatase titania in the presence of this vanadium. Now, if you try the same thing without the vanadium, you have to go to much higher temperature to get the anatase to form. So in fact, the vanadium is catalyzing the crystallization of the titanium in this case, from the amorphous state to the crystalline state. There's also apparently some small structure here associated with a different form of titanium, namely the Brookite form. So the Raman spectroscopy, of course, can tell you all these things are there because it more or less sees everything to some degree. And the value of doing measurements at different laser wavelengths is we hope ultimately to be able to see everything that might be in our inhomogeneous catalyst mixture. Okay, so I'm going to conclude by just acknowledging the students and postdocs and collaborators who did this work. And as I said, there are 3 posters in this evening's session where you can learn more detail about what I introduced in the talk today. Thank you for your attention.
Okay, so we have time for, let's say, 2 questions and maybe 3 quick ones. Okay, first question. Okay. Just go, Joe, by the mic.
I have a loud voice.
Okay.
Raman radiation typically has a lot of power with it. How do you account for that it might be doing some of the chemistry you're seeing, particularly using UV radiation?
Sure. Okay, so we've worked very hard to look at that problem. So, in fact, we developed this fluidized bed reactor so that we can essentially stir the material and allow the flushing of fresh material into the laser beam to take care of this damage problem. The biological people have known this for years, and they basically have flow systems. It's harder to do that with particles and gases, so we essentially produce an internal flow. And there's a number of papers that I can direct you to where we look specifically at these kinds of effects. And we can make it happen if we want to, but we're quite aware of the issue.
Okay. One more question? 1, 2. Okay, I have a very short question. In the first part, you were presenting the coking.
Yes.
And the coking, you did it on 2 different ZSM5, different silicon volume ratio by putting methanol and then shining the laser to heat it up. Did you see any evidence for de-elimination of the zeolite during this treatment? Because you are going to produce a lot of water which will remain in contact with the zeolite.
Right, so there were no measurements that we did specifically to look for de-illumination. We would not be able to see it by Raman spectroscopy alone. So we would have to presumably do NMR or something like that, which is sensitive to the form of the aluminum in the zeolite, and we have not done that.
I think if you look at the Raman spectrum, so maybe if the illumination occurs, there should be some change in Raman spectrum, especially internal vibration. So maybe.
Right, so the response was that from the zeolite vibrations alone, we might be able to tell whether there was de-illumination. But I suspect it would have to be quite large for us to be able to be sure that, in fact, that had happened. In fact, massive, I would say.
Okay. Thank you again for this nice